We live in a noisy world. From lawnmowers to jets to babies, noise follows us everywhere. So when I told my editor we were making a video about a near-silent engine that can accelerate in deep space for years using almost nothing, her response was simple. No way! Like, how quiet are we talking? The thing is, it's really quiet. Like, quieter than you can imagine. Welcome to the quietest engine that can take us to the stars. It's me, and this is our channel. Let's start with a quick thought experiment. Imagine you're floating in outer space far away from any planets or stars. You have no air to breathe, no gravity to hold you down, and nothing to block your path forward. If you could just tap yourself ever so slightly and keep tapping, you could keep moving forever. Keep going without ever slowing down. Now imagine taking that idea and scaling it up to spaceship size. Well, believe it or not, this is exactly how propulsion works. An electric spaceship engine that whispers instead of roars and travels at a constant speed indefinitely. It is perfect for traversing the emptiness of space and will one day let us reach places that seem impossible today. In fact, this quiet little engine might just be humanity's best chance to get to the farthest reaches of our solar system. To understand how something so quiet can move a spaceship through the emptiness of space, let's start with a brief history of rockets. For centuries, humans dreamed of flight through the skies above our home planet. But it wasn't until 1926 that the first rocket reached space, thanks to the efforts of many scientists and engineers. And since then, these amazing machines have become relatively commonplace. But they aren't perfect. To understand why, let's take a closer look at a launch from the legendary Saturn V rocket, which flew astronauts to the moon. As the rocket takes off, massive amounts of fuel burn and explode at the bottom, shooting hot gas out of the base and sending the rocket skyward. The burning fuel produces intense heat and tremendous pressure. All of this energy goes into creating a strong downward flow that pushes against the ground and launches the rocket. This is called thrust. But while the fiery plume of smoke shooting out of the rocket's engine looks impressive, it's actually a waste. Every action has an equal and opposite reaction. So every kilogram of gas shot downwards must be balanced by an upward push on the rocket itself. This is what creates thrust and propels the rocket towards space. But once in space, there's nothing to push against, so the whole system falls apart. Of course, the good news is that a rocket doesn't need anything to push against in order to keep moving. Once a rocket is in space, it keeps moving pretty much forever. It just needs enough energy to keep going. This is where the trouble starts. When it comes to getting something off the surface of the Earth, the issue isn't getting it to speed, it's slowing it down. Because of this, rockets are designed to burn through their fuel quickly, giving huge bursts of thrust to counteract the effects of gravity. But once free of Earth's gravity, they don't need to go very fast. And the exhaust from their engines gets left behind in space too. So in essence, chemical rockets are blunt instruments. They burn fuel and oxidizer together and hurl the exhaust out the back at a few kilometers per second. It works beautifully if your goal is to escape Earth's gravity. But in the vastness of space, the rules change. With chemical rockets, you burn for minutes, then you coast. You can't keep pushing without carrying a mountain of fuel. And in space, mass is your enemy. In 1958, NASA faced this problem. If we wanted to go further, past Mars, past Jupiter, we needed something different. The solution was found in physics. For centuries, physicists had been studying electric charges called ions. Unlike normal electrically neutral atoms, ions have an electrical charge. This makes them ideal for use as a propellant, since it's easy to speed them up and control their movement. But this idea remained stuck in theory until computers and electric propulsion came along. In the 1960s, NASA started seriously looking into this new idea. What if instead of explosions, we use electricity? What if we could accelerate particles so fast, so efficiently that even a tiny trickle of thrust would build into enormous speeds? This is propulsion. It's as simple and as bizarre as it sounds. Take a gas like xenon, strip electrons off its atoms to make them ions, then fling those ions out the back at incredible speed, about 90 kilometers per second. That's about 200 times faster than the exhaust from a space shuttle's main engine. To give you an idea of just how much faster that is, a speeding bullet fired from a handgun leaves the barrel at about 450 meters per second. A speeding car traveling at 180 kilometers per hour moves at roughly 50 meters per second. By comparison, an I don't thruster's exhaust is traveling more than 18 times faster than a speeding bullet. To achieve these speeds, the gas is sent through a device called a plasma accelerator or I don't thruster, which consists of two large grids. The first grid accelerates the ions to a high speed, while the second grid focuses the beam into a narrow, powerful jet. When the ions exit the thruster, they slam into the vacuum of space and slow down. But by then, they've already accelerated the spacecraft by the same amount. Because momentum is conserved, the I don't beam and the spacecraft move together as one, causing the spacecraft to accelerate gently. Importantly, since the gas is electrically charged, it can be controlled precisely, allowing for better steering and course correction. It's even possible to fire multiple beams at once, making tight turns that would take hours with a chemical rocket almost instantaneous. Theoretically, I don't thrusters could run for months or even years, traveling farther and faster than any chemical rocket ever could. Now the challenge was proving that this strange idea actually worked. I don't propulsion lived in research labs and science fiction novels for decades. Then in 1998, NASA launched Deep Space One to test the concept. The little spacecraft successfully visited asteroid 9969 Braille and comet Borrelly, proving that I don't propulsion could survive deep space. Then in 2007, Dawn became the first spacecraft to use I don't propulsion for interplanetary travel. The twin spacecraft visited the dwarf planet Ceres and the asteroid Vesta, all with less fuel than a small car's gas tank because its thruster ran for over 2,000 days. Dawn or its successor could easily last more than a decade. And in 2020, a Japanese probe named Hayabusa 2 used I don't thrusters to perform a daring maneuver that brought it within 22 kilometers of the surface of an asteroid. Today, I don't thrusters are a common sight on satellites, quietly using I don't propulsion to make tiny adjustments to their orbits that add up to big changes over time. If you want to hear more about I don't propulsion, check out our podcast available on various platforms. You know, most people think of space travel as loud and dangerous. And sure, launching a rocket definitely fits that bill. But once a spacecraft is free of Earth's gravity, things get a lot quieter. There's no air to carry sound and no wind to push you forward, and no friction to slow you down. If you could just tap yourself ever so slightly and keep tapping, you could keep moving forever. Keep going without ever slowing down. An I don't thruster is such a slow and steady machine that on Earth it could even lift a sheet of paper. But in space, where nothing slows you down, that tiny push applied for months can send you flying faster than any chemical rocket ever could. Thanks to I don't propulsion, we now know that a spaceship doesn't need to roar to get where it's going. It just needs to keep moving forward, step by step, until it arrives. The real trick is finding a power source that can keep those steps up for years. Nuclear engines are the obvious choice, especially if they can be miniaturized. Currently, though, I don't thrusters are mostly used for smaller satellites. But in the future, we could see them powering larger spacecraft on long journeys. Missions to Mars could rely on electric propulsion to ferry supplies efficiently. Outer planet probes could travel faster and carry more instruments. And the most ambitious ideas, engines like Vasimer, could reach Mars in 39 days with the right power source. Vasimer is a variable specific impulse magnetoplasma rocket. It's basically an I don't thruster on steroids. With the right power source, Vasimer could reach Mars in just 39 days, compared to the 9 months it takes a typical ship. This engine uses magnetic fields to accelerate ions even faster than conventional I don't thrusters, and it can switch between high and low gear depending on the mission profile. Imagine a fleet of spacecraft powered by nuclear fusion, generating enough electricity to send massive ships roaring through space at incredible speeds, while still producing virtually no pollution. Nuclear fusion power would allow us to explore the solar system in ways we never thought possible. The real trick is finding a power source that can keep those steps up for years. I don't propulsion is the art of trading time for velocity. Chemical rockets burn their fuel quickly to get a quick burst of speed, but I don't thrusters hum quietly for years. If we really want to reach the edges of our solar system in our lifetimes or send robotic scouts to the nearest stars, this quiet blue glow might be our first real ticket. That's all for this episode. Don't forget to tune in next time to learn about another amazing technology. Thanks for watching.